Alrighty. So, before we get into that worksheet, let's take a look at the question here. So, a PT Cruiser is traveling faster than a VW Bug. So, now what can you say about those cars' accelerations? All you know is that the PT Cruiser is traveling faster. What do you think?
The PT Cruiser has a greater acceleration.
It could have. Anything else we could think about here? And that's kind of the standard answer, is that you'd think the PT Cruiser would have the bigger acceleration. Yeah.
I think that the accelerations can be the same.
They could be. And so, yeah, this is kind of, I don't know, stupid little trick question, so sorry about that. But for these questions, just because the PT Cruiser is traveling faster doesn't necessarily mean it has a larger acceleration, because we don't know a lot of things about this. We don't know when they started picking up speed. We don't know if the PT Cruiser might have started from a faster speed. So really the answer is just we don't know anything. Generally, you'll think that, you know, if they both started from rest, the PT Cruiser would have had to have a bigger acceleration at some point. But once again, we don't know enough to say anything for sure. So the answer is we just don't know. So have out worksheet number 6, please. We're going to talk about this for a little while. You might have noticed on Schoology that we have a group quiz tomorrow, so that's something that you need to make sure that you're ready for. You'll be grouped up with 2 other people, and you'll do the best you can on a little quiz. The best way to study for that is just to look over worksheet 5 and worksheet 6. Of course, worksheet 6 we'll go over today. Make sure you're okay with all that. And I'll throw some hints your way at the end of class when we're done going through worksheet number 6. So, let's take a look at worksheet number 6. I think we might as well just go through the whole thing. How does that sound? Because it's when you start, it's one thing to do these graphs without numbers or qualitatively, if you remember from the worksheet. But to do them when you have numbers is a whole new ball game. So we'll go through this nice and slow. And if you have any questions as we make our way through, please let me know. Again, one thing I did not put on the video last time, but I told you after the video was done, was on your formula sheet, it tells you the difference between qualitative and quantitative. If you see the word qualitative, that means you need to solve the question without numbers, like just sketching a graph. If it says quantitative, that means you need to solve it with numbers. Most of the graphs on worksheet 6 you have to use numbers with, so those are quantitative. So let's start with the front page. Actually, we did the front page together. So let's go to page 2. All the way to problem number 3. So number 3 is a velocity time graph. And we have to draw what this velocity time graph is going to look like. And it says we have to draw it quantitatively. That means with numbers. Now this is all part of the same scenario from the previous page. And just as a quick reminder, the scenario is you're traveling on a dark stretch of road. You're going at 25 meters per second, which is roughly 50 miles an hour. And you eventually slam on your brakes because you notice something through the fog. So, for that scenario, the time starts immediately when you hit the brakes. So, from the beginning, you begin your slowing down. So, on our velocity time graph, we know that we start with a speed that's rather large, 25 meters per second, And because you slam on your brakes, you're going to be slowing down that whole time. So the graph's going to look something like this for the velocity time graph. Now, of course, we have to do this quantitatively, so we got to add some numbers in there. So up here, this would be 25, because that's how fast you're starting the instant that you hit the brakes. And you come to rest 4 seconds later, so that means this is your 4 seconds. So that's number 3. Number 4 says, on that graph, shade in what represents your car's displacement while braking. Who can tell me what that is on a velocity time graph? Exactly. So it's below this line. It's, according to your formula sheet, your distance traveled is the area trapped by a velocity time graph. So this would be that trapped area right there. And that's all you would need to do for problem number 4. Thanks. Problem number 5 then says, use the graph to figure out how far you went. Well, this is a triangle. And if you remember from geometry, or whatever class in math you had before that, when you looked at triangles, area of a triangle is 1/2 base times height. So 1/2, the base is 4. The height is 25. So 4 times 25 is 100 times 1/2, and that's 50. And because it's a distance, it's measured in meters. You would also get meters if you threw in the units, back here, because 4 is time, it's in seconds. 25 is meters per second. So those units would come right out of that. Questions on number 5? All right, we're cruising right along, just like that PT Cruiser, whose acceleration we know nothing about. Number 6, in order to draw your acceleration versus time graph, you need to determine your car's acceleration. Do this, and then construct an acceleration versus time graph. So, how in the heck are we supposed to calculate acceleration? All we have is a stupid little velocity time graph. What do you think? It's okay, it's early. Yes?
Well, if you know the slope. Oh, never mind.
You're right on the money. Keep going.
If you know the slope and the velocity time graph, then you know the acceleration.
Exactly. So just like on your formula sheet, it says the slope on a velocity time graph equals a, or acceleration. All we got to do is find this slope. That's what your acceleration is. So rise over run is slope. So I'm going down 25. So that's going to be negative 25 for the rise. The run is 4. And when you plug that into your calculator, you're going to get negative 6.25. I think, yep. And that's meters per second squared, because these are the units for acceleration. And just like the units up here, if I threw the units into my quotient, those units would pop right out, because this is 25 meters per second. This is 4 seconds. So it's like you do the fancy thing where, meters per second, and because this is on the bottom, it's like multiplying it by 1 over seconds. So your units would be meters per second squared, and that comes right out. So if I got to put that on my acceleration time graph, it's a negative value, so I'm going to have my acceleration be down here somewhere. And that's what you would have for your acceleration time graph. Questions on the graphs? Yes? Oh, you're good to go? What's that? Okay. Alrighty. So, that's how we solve this problem with graphs. Now we're going to do the whole thing again, but without graphs. From what I remember, most of you guys liked algebra better than geometry, so most of you are probably going to have an easier time with the equations as opposed to the shapes on the graphs. Let me see those hands again. How many people like algebra better than geometry? How many people prefer geometry? Well, that's actually pretty close. Might actually have more geometry lovers in here than algebra. So, number 7, this is the same scenario. We're still starting at 25. We're still slamming on the brakes and coming to rest 4 seconds later. Number 7 says, use the equation you developed for the displacement of an accelerating object. Determine how far your car traveled during braking. So essentially what we're doing in number 7 is the same thing that we did in number 5. Except number 5 we used a graph to figure out that displacement. So the equation that I showed you is this. Now, on your formula sheet, this equation is actually listed with y's instead of x's. The reason for that is, as we go forward, usually this equation is used vertically, because when objects are dropped vertically, they always have an acceleration. So usually we're dealing with this up and down, which is why I list them as y's on the formula sheet. But for this scenario, you can think of them as x's, horizontal positions. It's the same either way. So, this is the equation we have to use because we're slowing down now. We don't have a constant velocity. So if we want to figure out our position, how far we've gone, we got to go to this guy. We have no choice. This is the only position equation that includes an acceleration. Now, as I mentioned last time, this value here is almost always going to be 0. It's very rare that you're given a story problem that does not begin on the origin. Unless it specifically says that you're starting away from the 0 point, you can assume that this value is nothing. You can assume you're starting on the origin. I also said that oftentimes the original velocity is 0. Well, in this case, it's not. In this case, we do have an original velocity because we're starting at 25 meters per second, and then we slow down over time. We figured out what our acceleration was using the graph, so we should be able to just straight up use this equation to figure out how far we've gone. So let's see here. Original velocity is 25 meters per second. The time is 4 seconds. That's how long that we're slowing down. And then we've got 1/2. And the acceleration that we calculated in number 6 is negative 6.25. And then again, time is 4. So those are your numbers. And if you plug those numbers into your calculator, you're going to end up with 50 meters. And 50 meters matches up with what we found in problem number 5. Again, we're solving the same question 2 different ways, with graphs and with equations. So number 8 says, compare your answers. Hopefully you got the same thing. Explain why they are the same or different. Hopefully they're not different. They're equal. And they're equal because they're just different ways of solving the same problem. No one way is better than another. And that's the neat thing about physics. And the deeper that you go into physics, the more ways there are to solve different problems. You might find that you're better with shapes and graphs. So then solve this problem with shapes and graphs. If you like equations better, solve it with equations. And when we really get into the nitty-gritty of this class, you'll find out that not only can you solve these problems with equations and graphs, but you can solve them with energy, or you could solve them with momentum equations. There's so many different ways to solve these problems in physics that you can really tailor your solution to how you feel comfortable with the material. It's one of the great things about it. So, that's one of the big problems. Let's start the next one. So this is on page 3. So now you're cruising along on another dark stretch of highway. And you're going at 30 meters per second, which is about 60 miles an hour. You notice a thick fog up ahead. Must love driving in the fog there. It takes you 0.5 seconds to react. Then you apply the brakes, come to a stop 3.5 seconds later. So we're kind of running through the same process for this as we did in the last one. We got to do these problems with graphs, and then we got to do them with equations. So, construct a quantitative velocity time graph. That means we need numbers. So we begin at 30 meters per second. So that is our starting velocity. So I'll just put that right here. 30 meters per second would be on the top there. And we're not slowing down right away here. We have to make sure we take note of that. In the last question, we applied the brakes immediately, so we were slowing down the whole time. This is not that same case. This is different. Now we keep that 30 meters per second for a little bit, and then we hit the brakes. So we're going at that speed for a little while, and then after that, we do hit the brakes and come to a stop. Because remember, it takes us 0.5 seconds to react to the fog. So in terms of our numbers then, this would be 0.5 seconds here. And it looks like we come to a stop 3.5 seconds later. So that would be a total of 4 seconds at the end there. So that would be our velocity time graph. Any questions on how we got this picture? Okay. So then, number 3. Oh, number 2. Shade in what represents the car's displacement. No surprise here, it's the same as before. On a velocity time graph, the area trapped by your graph represents your total distance traveled. So you would just shade that area in. Now for number 3, when we're actually calculating this area to get our distance, we have to be careful because we don't just have a triangle here like the last one. We've got 2 shapes. We've got a little rectangle and we have a triangle. So we have to take both of those areas into account. So we'll just add them together. This is a rectangle. The area of a rectangle is base times height. So that's going to be 0.5 is the base. The height is 30. And to that, we have to add the area of our triangle. Of course, that's 1/2 base times height. So it's going to be 1/2. The base here, what is my base? 3.5. Why is it 3.5 and not 4? Exactly. So when you're doing these graphs, make sure you're paying close attention to that. This base is 3.5. The total distance, the total time is 4. But the part that's just the triangle is 3.5. And of course, the height, just like before, is 30. So then we do a little bit of math. And when we do that little bit of math, we're going to get 67.5, I think. Unlike all the math that we've done a couple months ago, this doesn't matter if you're in degree mode or radian mode. So feel free to be in whatever mode you want for these. That just matters for sine and cosine. So that is our distance traveled that we found by the graph. Number 4 says, in order to draw your acceleration versus time graph, you got to find your car's acceleration. So let's do that. This is my velocity time graph. Once again, the slope represents acceleration. What's the slope of this line? 0, exactly. So the first half second, you've got an acceleration of nothing. Then, of course, we got to find the slope of this line. Rise over run. I'm going down 30. So my rise is negative 30. And I'm going across 3.5. So when you do that math, you'll get negative 8.57. And meters per second squared are the units for acceleration. Thus, for your acceleration time graph, you're going to have a fancy horizontal line in the negative somewhere. And if this is a quantitative graph, you got to point out that this is negative 8.57 here. And that's all she wrote for that. Further questions on the graphs? Is this starting to make some sense? Good. Number 5, this is an interesting one, and this is the most difficult question probably on the worksheet. So number 5, we're doing the same thing that we did before, except now we're using equations, just like the end of the last big problem. This is a little bit more complicated than that one, though, because we're not just slowing down the whole time, like the previous problem. We've got 2 different phases of motion here. We have to be careful we take both of those into account. So yeah, that's basically what the description says. So the first phase of motion, you are traveling at a constant velocity. I'll label it first phase. So when you're traveling at a constant velocity, the equation that you use is this one, x equals vt. So our velocity is 30. And we keep that velocity for 0.5 seconds. So when you do that math, this is one I can actually do in my head. My wife's really good at doing math in her head. I'm not. 15 meters should be the answer that you get for that first part of the motion. So this is how far you've gone for that half second that you're traveling at that constant speed before you apply the brakes. The second phase is the part when you're actually slowing down. And of course, for that we got to use the long intimidating equation. What do you suppose this is going to be for this problem? Why? Yeah, I suppose. That's what I said. And what I said was, unless it specifically tells you that you're not starting at the origin, you can just assume that this is 0. And that's what's going on here. It doesn't say that we're beginning at some point other than 0, so we can just assume that's true. Now, just like the last one, we do have an original velocity here. That's 30. And we keep the entire time that we're slowing down, remember, is 3.5 seconds. And that's what this time represents. This would not be 4 seconds because this equation is something we just use for the portion of time that we're slowing down. So while we're slowing down, we're doing that for 3.5 seconds. We already took into account that first half second over here. 1/2, and of course the acceleration that we found from the previous one was negative 8.57, and time once again is 3.5. And after all that fancy math, you'll end up with a distance of 52.5 meters. So, 15 plus 52.5 should be 67.5 meters. And no surprise, that's exactly what we got in the previous problem, in number 3, when we calculated the distance from the area that we shaded on the graph. So once again, to answer number 6, both ways solve the exact same problem. They're just different mechanisms that we can use in order to solve for that particular scenario. It's like having 2 tools that are fine for doing the same job. Use whichever one you like. It doesn't really matter. They're both equally effective. Further questions on the worksheet? Okay. I'm going to let you hang on to that. When you're studying for the quiz tomorrow, just look over worksheet 5 and 6. I'm also going to give you a few hints up here, just to make sure that you're as prepared as you can be for the quiz. And it's not something that's real big and long. It's going to be rather tame, I think. You don't have to take notes. If you want to have them for reference, you're welcome to, but if you're drawing those, I'll give you just a minute to do that. If not, no worries. The main thing that's going to be emphasized on the quiz tomorrow is you need to know the relationships among these graphs in terms of their slopes and their areas. And you can have your formula sheet with you, but the more you hear this, the better it's going to be for you. On a position time graph, let's say it looks something like, let's just say we have something that looks like this. What does this tell us about velocity? Is it positive or is it negative? Positive, exactly. because we've got a slope that's positive. I'm sure that wasn't important. So the slope on this graph always tells us what velocity is. You need to make sure that you're aware of that. As this slope changes, your velocity will change too. That's the thing that you can tell from this graph. On a velocity time graph, maybe it looks like, and these are not related. I'm not going from here to here. This is independent. If I have a velocity time graph that looks like this, I can solve for two things using this graph. I can solve for the distance traveled in the object simply by calculating this area, and I can solve for the acceleration of the object by calculating its slope. In terms of the acceleration time graph, there's really not a whole lot that we use this for. On your formula sheet, it will say that the area trapped by an acceleration time graph will tell you the velocity that your change in velocity. So how much speed have you gained from here to here? That's what this area tells you, but it's pretty rare that we use that. These three things over here are more important. This area tells you distance, this slope tells you acceleration, this slope tells you velocity. So make sure you're aware of those things. Finally, I'm just going to draw some stuff on the position time graph. Make it nice and big. So let's say I've got a position time graph that looks like this. If I wanted to calculate my instantaneous velocity at, say, 3 seconds, what do you suppose I'd have to do? Like how fast I'm going right at that moment. Yeah, exactly. You'd use x and you'd use the time in order to figure out what the slope is. We know the slope on this graph represents velocity. So whatever this slope is during those 3 seconds tells us what your speed is at that particular moment. So it's not just about looking at the graph and then saying this slope represents velocity. For a particular moment in time, that slope tells you exactly how fast you're going at that particular instant. That's different from, well, let's quick say, how fast do you suppose you're going at 5 seconds? What's your instantaneous velocity there? Nothing, because it's a slope of 0, and slope represents velocity. Now, if it said calculate average velocity at 7 seconds, remember that your average velocity is simply your change in distance over your change in time. So all you would do to calculate average velocity is figure out what distance you ended at. Maybe it's 6 meters. So 6 meters would go up here. The total time that you've been traveling is 7 seconds. So then your average velocity would just be 6 over 7. So when you see these things, I just want to make sure you're not overthinking them. All right. Oh, good. 3 minutes. Questions on the difference between instantaneous velocity and average velocity? Okay. And the good part is, if you forget, hopefully your 2 other group members will remember. Last thing. let's say we have a position time graph that looks like this. You do have to know, once again, that slope represents velocity, and you have to be aware how that velocity changes as time goes on. So, what can you say about the velocity in the beginning here, if anything? Is it big or small? Big, because it's a big slope. Is it positive or negative? Positive, because it's a big positive slope. So what's happening from the beginning up until this point? Are we speeding up or slowing down? We're slowing down. And at this point, we're at rest, because this is a slope of 0. Now as time continues, you can see that slope is then growing in the negative direction. So then that means our velocity is growing in the negative direction. By the time we get here, we're moving awfully fast. So you got to be a little bit aware of how position time graphs affect velocity when they're curvy and not just straight lines. So, all right, that should be good. You guys are going to do just fine on the quiz. Don't sweat about it. And if you're not feeling confident, just look over worksheet 5 and 6, and you'll do just fine.
When is the quiz?
Tomorrow.